Hello everyone, welcome to topic 3.13, Beer Lambert Law. In this, you should be able to explain the amount of light absorbed by a solution of molecules or ions in relationship to its concentration, path length, and molar absorptivity. We do have another equation in this one, which is given here. This is given on the equation sheet, so you need to know how to use it. Okay, and so we will discuss that in these notes. One way that we can measure the concentration of a colored substance is by seeing how much light can pass through it, or how much light is stopped by a solution. The measure of light that is stopped by or absorbed by a solution is referred to its absorbance, because it's being absorbed by that solution. A spectrophotometer or colorimeter, because it's looking at the spectra that's being absorbed or the colors that are being absorbed, can be used to measure the absorbance. Below is a very simplified schematic where we have a light source emits specific energy wavelengths into a colored, and it's not always red, just a colored solution. Some of the light at specific wavelengths is released and it is detected, and then you get a graph of some sort or numbers of some sort that you can then generate a graph with. The more concentrated the solution is, the less that light can pass through the solution. Concentration is a measure of the amount of particles that are distributed in a solution. You can think of this as how densely packed the particles are. Concentration is measured in a lot of ways, but we will use units of molarity, and this has been discussed already. To review, molarity is the moles of solute divided by volume of solution. Solute is a term used for the substance that is dissolved. Most commonly, we use water as a solvent. The solute and solvent together give you a solution. A solution with water as the solvent is an aqueous or aquatic, right? Aqueous solution. The unit M is for molarity, contains 2 units, and means moles per liter. Molarity can be used as a conversion factor because it has 2 units, moles and liters. For example, if I have 2 liters of a 0.25 molar solution, how many moles of solute are there? Well, you can use the concentration as a conversion factor. You can also just plug it into the molarity equation that we have done in the past. Okay. Different colors of solution absorb different colors or wavelengths of light. If we are using a red solution, so like an iron solution, a lot of iron salts have a red solution, we should choose a green light with a wavelength between 560 and 520 nanometers. That is because if it's a red solution, that means it is emitting that light. It is not absorbing it. Well, you want to look at what it's absorbing, and it's usually best absorbing its complementary color because you're seeing its opposite the strongest. Okay. So for colored solutions, absorbance can be used to measure the concentration of solutions. So to do that, there's a couple different steps that we can take. First, you will need to determine the best wavelength to use to measure your sample. To do this, you will place your sample into the spectrophotometer or colorimeter and generate a graph of absorbance on the y-axis versus wavelength on the x. Your independent variable is wavelength, so you are the one that is setting this on the colorimeter. You're telling the colorimeter or spectrophotometer, hey, put out light in these wavelengths. And then it will detect the absorbance and plot it for you. The best choice for a wavelength is the one that is highest or closest to 1, which in this case would be this one at 620 nanometers. Once you have this, you're going to use this wavelength for future data collection, because that's the one that the solution is going to absorb the best. So it'll give you the most accurate data. You then will create a calibration graph with standard solution concentrations and their corresponding absorbance value. So you do like 0.1, 0.2, 0.3, 0.4, or whatever molarities, so that like these, you would have decreasing concentrations or even increasing concentrations. It's easier to do decreasing concentrations though, because you just add water, to generate a graph that looks like this. Okay, the graph should result in a linear graph, and it gives you the molar absorptivity constant, which is here. The absorbent, the more concentrated a solution is, the more light that is absorbed. The Beer Lambert Law describes this absorbance with A is equal to epsilon B times C, and those are given here. Please make sure you pay attention to your X and Y axis units, especially for concentration, because a lot of the times you're working with very, very dilute solutions. Okay, so you make the solutions and you set what those concentrations are. You then put them into the spectrophotometer, and the computer measures each of those absorbances, and it gives you a linear graph. Once you have this graph, you can measure the absorbance for an unknown solution or an unknown sample and determine the concentration. By getting the absorbance from the computer, you can go back and check on your graph what a concentration is, or use the equation of a line. The path length, term B from up here, is the width of a cuvette, which are what these are. These are little square test tube thingies that sit in the spectrophotometer. These are generally 1 centimeter in length to hold it all constant. Makes the math really easy because then you're just multiplying by 1. When you calibrate the spectrophotometer, you should always start with a blank, and that is only your solvents. It's usually just pure water. By calibrating the spectrophotometer with a blank, it removes the data from the solvent. So like you're saying, hey, this is my baseline value, and now we're going to look at the concentration of a specific solute in this thing. So if the water gives like interference data, you're getting rid of it by using it as a blank. So it's kind of like tearing for your spectrophotometer, like you tear a digital scale to zero out to the weighboat that you use or whatever's on there, a beaker. This, by using a blank, you're setting a baseline 0 for the machine, and then you're changing your concentrations from there. You're telling it what concentration of 0 looks like. Okay, let's look at the I-dos. Based on the provided graph, if the absorbance of an unknown concentration of a solution is 0.34, what is the molarity of the solution? So we go to 0.34 and approximate it here. We draw over and come down. We could also plug it into the graph. Like if you wanted to plug it into this, y is equal to 0.113x. You're solving for x because this is your y value, or you can use the graph, and you should get something around 2.9 or 3.0 times 10 to the negative 6, because that is what it's telling you the units are, molar. So times 10 to the negative 6 molar, or you can switch out the times 10 to the negative 6 and put micromolar. Okay, so for this we have solution X has this absorption graph over here. What would be an appropriate length to gather the absorption data? What is the color of light absorbed? Predict the color of the solution. So I want you to pause the video and do A through C yourself first, and then we will check in after. Okay, so you should have paused the video and now you're resuming because you're ready to check your answers. So an appropriate wavelength to gather the absorption data would be the highest peak, which is up here. And so reading the graph, you should have gotten 620 nanometers, because that is where the absorbance is the highest. Or you could have done like 619 or something if you thought it, 618 if you thought it was a little bit higher just before. Now, what is the color that is being absorbed? So for that, you needed to have gone back up here to these. So 620 falls within the orange. So you should have gotten orange here. Okay, predict the color of the solution. So if it's absorbing orange, that means that it is colored blue because it is complementary colors. So it should be a blue solution. Okay. From here now, you are going to answer D. A solution with an unknown amount of the same solute X was prepared and graphed as shown. How is the new solution, unknown concentration, which is red, different from the first one? How is it the same? So please pause the video. Resume when you're ready to check your answer. Okay, so you should have gotten that these are still the same compound because the shape of the graph is still the same. So they should have the same color solution and still absorb the same color light. These are different because the new solution is half as concentrated, because the absorbance values are half of the original graph, and you can go through all of them and check, but checking a couple points, 0.2 to 0.1, 0.8 to 0.4, so all along this it's half. Okay. So now move on with the you-dos, check your answers, and thank you for tuning in.